Ants are remarkable navigators. In some species, such as desert ants, each forager learns long routes between the nest and food sources, and they do so using vision. It is believed that ants memorise the appearance of the scenes projected on their retina while running along the route.
The idea is that the memories of the scene are stored in the ant brain in an egocentric fashion. That means the ants must be facing forward, as in training, to recognize the scenes. If the ant is facing in the wrong direction, the scene must appear unfamiliar to her.
However, we have a problem. Ants sometimes drag heavy food backwards, but still manage to find their nest. According to the theory, when walking backwards, the scene must appear entirely unfamiliar to the ant. So the question is, how do they still manage to navigate backwards all the way to their nest?
To answer this question, we first wanted to test whether ants can recognize the perceived visual scenery along a foraging route, but when they are walking backwards. And for that, we designed a simple experiment. We let ants run along a foraging route that included a sharp 90-degree turn. And after 1 day of training, we captured those ants, which were familiarized now with the foraging route, and released them just in front of that sharp turn.
Ants running forward with a small cookie in their mouth displayed a sharp turn, indicating that they were using visual memories of the scenes. However, ants going backwards with a large cookie did not turn, but carried on in the wrong direction. It thus seems that ants do not use their visual memory of the scene when going backwards.
So it looks like the hypothesis is safe. Ants seems to use the scenes only when going forward, as in training. But then, how can they manage to find their nest when going backwards? Fortunately, the ants themselves told us the answer. They displayed the solution right in front of our camera.
Sometimes ants going backwards would let go of their cookie to turn around and peek forwards. They would then come back to their cookie and resume dragging it backwards, but this time in the correct direction. This suggests that they might align their body forwards to recognise the scene and to recover the direction, but that they can then memorise this direction to subsequently follow it backwards.
This behavior is interesting in itself, as it implies a synergy between at least 3 types of memory. The long-term memories of the route sceneries, the memory of the new direction to follow, and also the memory of the cookie left behind.
To get a full story, one still needed to consider how the ants managed to maintain their direction once walking backwards.
We suspected that the ants were using celestial compass cues to maintain a straight backward path. To test for that, we used a century-old but simple experimental technique. We took a mirror in order to reflect the sun, and from the ant's point of view, the sun suddenly appeared at the opposite side of the sky. As soon as the sun was mirrored, the backward walking ants displayed sharp turns, which indicates that they were relying on celestial compass cues while they're walking backwards.
It's worth noting, ants could maintain their direction of movement not only when going backwards, but also when going sideways, forward, or whatever their body orientation.
These results suggest that ants built a representation of direction centered not on themselves, but on the world. Until recently, we thought that ant navigation was a product of distinct stereotype strategies. Now, we see that their behavior results from the orchestration between multiple representations and involves the communication between different brain areas, which we discuss in the paper.